The confusion matrix dashboard provides two synthetic generators with adjustable sliders to control distributions of positive outcomes in red and negative outcomes in green. The horizontal axis is prediction score. The dual unimodal distribution puts positive outcome events and negative outcome events in bell curves. Use the sliders to adjust the heights of the curves, their locations along the prediction score axis, and their widths. In the stacked bar graph, watch the green negative predictions climb over the red positive predictions, or watch the reds slide underneath. The tan curve is the ratio of red positive to total predictions at each bin. It's called the PPR, Positive Prediction Ratio Curve. Wiggle the sliders to make this curve dance. Notice that the value of positive prediction ratio is always 1/2 where the red and green outcome distribution curves cross. Now let's look at the ROC curve. The ROC curve bends more sharply when the positive and negative distributions are well separated. Then, the area under the curve drops to 1/2 when the distributions are not separated at all. Notice how the true positive, true negative, and false negative ratios remain stable when you change the heights of the bell curves but not their shapes. When the positive and negative distributions are perfectly separated, then the false positives and false negatives can be eliminated if we put the decision threshold between them. This leaves only correct predictions, the true positives and true negatives. When the positive and negative distributions are not perfectly separated, then you can still eliminate either false positives or false negatives, but not both. For example, if you want to zero out false positives so you don't mistakenly predict a positive outcome for any actual negative samples, then you can set the decision threshold over to the right. But you pay a penalty of high false negative rate. You fail to correctly predict a whole bunch of actual positive outcomes. A second class of synthetic data source is approximately linear. This data generator uses a constant number of samples. The first slider tells how those samples overall are distributed between lower versus higher prediction scores. The second slider controls the proportion of condition negative outcomes in green to condition positive outcomes drawn in red. Finally, the third slider controls how positive and negative outcomes are distributed across prediction scores. The distribution is designed so the positive prediction ratio curve is always linear, meaning that the ratio of negative outcomes to positive outcomes is a uniformly growing or shrinking fraction as prediction score increases across the graph. For starters, let's start out with an even distribution of prediction scores. We'll set the fraction of true positives at 50%. As we adjust where positive versus negative outcomes occur, we see that as positive outcomes get disproportionately more high prediction scores, the true positive and true negative rates get better, and the false positive and false negative rates decrease, which is good. The positive prediction ratio curve slopes upward. Steeper is better. And the ROC curve bends upward. Here we get an area under curve of all the way up to 0.8. Again, we can adjust the decision threshold to trade off true positive rate versus false positive rate, true negative rate versus false negative rate, and precision versus recall. Next, let's adjust the top slider to change the distribution of prediction scores. In order to maintain a linear positive prediction ratio curve, now the shapes of the positive and negative outcome distributions have to bend a bit. Here's a situation where the prediction scores are skewed highly toward the low end, but as score increases, a greater and greater fraction of outcomes are true positives. And check this out. If we slide the decision threshold all the way to the left, then we predict every sample to be a positive. The PPV, or positive predictive value, which is the same as precision, is 0.45, which is what we said is the fraction of condition positive samples. NaN means not a number for the negative prediction conditional use measures. That's because there are no negative predictions at a threshold of 0, and the denominator of these terms is 0. In computers, that impossible fraction is called not a number. The reverse happens if we kick the threshold all the way up to the rightmost bin. Now it's the false omission rate that becomes 0.45. That's the fraction of red positive outcomes overall that are now predicted negative. Play with the synthetic distributions in the confusion matrix dashboard in order to develop your own intuition about how the various terms of a confusion matrix behave as you slosh positive and negative predictions and outcomes along the prediction scale. When you find yourself dreaming about data like this, that's when you really understand it. Interactive visualizations can help.